So we have a number of molecules in nature. So any carbon compound that is normally actually extracted from a living tissue is called as a biomolecule, a living structure, a living molecule, any organic molecule or any carbon compound that is extracted from the body of a living tissue or from the body or from a living tissue is called as a biomolecule. Now, we'll pass on to this one. So I mentioned all the carbon compounds that we get from the living tissues can be called as biomolecules. Then what is the method of obtaining these biomolecules? Then how to know the various types of biomolecules in the cytoplasm? Simply you have to take a particular tissue, ground the tissue well in trichloroacetic acid. Trichloroacetic acid. The living tissue is ground with what is called trichloroacetic acid. So once it is being ground fully, we have received what is called a slurry, a paste. Just not a paste, we can say a semi-fluid structure. If this slurry is normally filtered or strained by using what is called a cheesecloth or a cotton cloth. When it is allowed to pass through this cheesecloth or cotton cloth, we can get two types of fractions. One is that one completely dissolved in that medium. Another one is being retained on the surface of the cloth. The one which is not being filtered. The one which is completely dissolved and filtered. So the first one is called acid soluble pool or simply called as a filtering. When we are just filtering the fluid, one part of the fluid is completely filtered and some part, a solid part, is normally retained on the surface of the cloth. So we can have two types of fractions. One which is called acid soluble pool, or we can say soluble acid. Another one just what is called acid insoluble fraction, because we are using the acid, trichloroacetic acid, for grinding. So one is what is called acid soluble pool, the liquid, the filtrate. Another one what is called acid insoluble fraction, normally called as retentate, the one which is being retained on the surface of the cloth. Now, actually, we have received, even the scientists have observed thousands of organic molecules from what is called the acid soluble pool, and those which are completely filtered. That means they are much smaller molecules, that is why they can pass through the openings at the pores of the cloth so that we can receive the filtering. And similarly, when you are burning a living tissue, for example, when a dead body is burned, you know that all the carbon compounds are oxidized to form a gaseous state, either in the form of that one carbon dioxide or in the form of water vapor, and all should be removed. So while we are burning a solid organic body in the form of dead body or plant body, so we have all the carbon compounds get oxidized to form a gaseous state, either carbon dioxide or water vapor. They should be simply removed. The remaining is called as an ash. So the remaining is called an ash. And this ash contains simply the inorganic elements, because we removed already the organic components as well as water. The remainder is nothing but actually the inorganic elements in the form of calcium, magnesium, potassium, sodium, etc. So if you're taking just, actually I mentioned already, we have thousands of compounds we have in the acid soluble. If you analyze the nature of the components from the acid soluble pool, and they show a molecular weight ranging from actually 18 to, that is 800 Dalton. So this is the molecular weight of actually the substances which are being filtered. That's why they are much smaller. That's why they can pass through the pores of the cloth. So, and those compounds which are found in the acid soluble pool have a molecular weight ranging from 80 to 800 Daltons. So those molecules below this range are simply considered as micromolecules. And those above this range simply we can see the macromolecules. This is a general statement I am saying, but we have different statement later. So anyway, the molecules which are being filtered, found in the filtrate, are simply having the molecular weight ranging from 80 to 800 Daltons. Now, what are the components? So this is about, actually we have thousands of components in this acid soluble pool. Now, what are the components which are being retained, the compounds? in the acid insoluble fraction. So in the acid insoluble fraction, we have only four different types of macromolecules or biomolecules, biological molecules. One, the polysaccharides or carbohydrates. Two, the proteins. The third one, the lipids. And finally, we have the nucleic acids. So only these four components are being retained in the written nature. That is, which are not being filtered. They are considered as macromolecular fraction, or we can simply say acid insoluble fraction. So we have polysaccharides, that is nothing but the carbohydrates. We have the proteins, we have the nucleic acids, and also the lipids. They are all being retained while they are allowed to be strained through the cotton cloth or cheesecloth. Now, and these compounds which are being retained are actually not being filtered, having a molecular weight just nearing about 10,000 Daltons or above. So these are all larger molecules having molecular weight. See that one. So they have the molecular weight in the range of 10,000 Daltons or above. Though we are just actually including the lipid molecules under this category because they are all being retained. But normally, if you are taking the molecular weight of the lipids, then they are just in the range of only 800 Daltons. So even that is considered as a micromolecule. But why we are considering these lipids as macromolecule along with polysaccharides, then proteins and nucleic acids. So along with these three, we are considering this one also a macromolecule, though the molecular weight of lipid is actually less than or not exceeding 800 Daltons. Now, actually, and before coming to this one, just why are they included? I will come to this later now. Once again, I have to show the slide also. Then we can classify the biomolecules into two types based on the molecular weight. Those having low molecular weight less than 1000 or less than 800, and those having the molecular weight above 1000 up to the range of 10,000. So accordingly, we have two different types of biomolecules. One, the biomicromolecules. Number two, the biomacromolecules. The biomicromolecules also simply called as biological molecules. See, micromolecules are simply biomolecules. And here, I mentioned already, those molecules which have a molecular weight less than 1000 Daltons. You see, the lipid is also less than 1000 Daltons, but we are including lipids under macromolecular fraction. I will give you the reason now. So, those which have molecular weights less than 1000 Daltons are coming under the category of micromolecules. And the next one, biomacromolecules, and those which are found actually in the acid insoluble fraction. Acid insoluble fraction. And those micromolecules are found in the acid soluble fraction. And here acid soluble pool we can see. Now, those which are found in the acid insoluble fraction and having the molecular weight in the range of 10,000 Daltons, I mentioned already above and above, they are considered as the biomacromolecules found in the just what is called the fraction, acid insoluble fraction, having the molecular weight above 10,000 Daltons. Then I mentioned already, so except the lipids in the insoluble fraction, that is the biomacromolecules, all others are polymeric substances, nothing but a polymer. A number of monomers are joined together to form, excepting the lipid. The number of monomers in a lipid molecule is less. The number of monomers in the case of proteins, nucleic acids, or even just in the case of carbohydrates is much more on the polysaccharides. So the number of monomers less in the case of lipid. That's why it's not considered as a polymeric substance. And all others, the carbohydrates, proteins, and nucleic acids, they're all considered as polymeric substances because they're all polymers. Now, why actually the lipids are included in the macromolecules, though they have the molecular weight less than 800 Daltons? See, so though they are all actually having a molecular weight less than 800 Daltons, they are not found as such as fats and oils, but also they form the components, or they are arranged into structures. They form the structural components of, that is, animal tissue or animal cell as well as plants. So that is why they are included under the macromolecular arrangement. So they are not present as such fats and oils, but also they are arranged into some membranes, the outer membrane of the cell. and also the membranes of the organelles. And while actually we are grinding a tissue, what will happen? The cell membranes and the organelles, simply you know that one, the membrane, the cell membrane, and other membranes found in the cell organelles, they are being broken into pieces and also separated along with what is called acid insoluble fashion. They are not being filtered. That is the reason why we are including the lipids also under macromolecular fraction or what is called acid insoluble fraction. Though they have low molecular weight, they form the structural components of cell membrane and also the membranes of other organs. So while we are grinding the tissue, and then what will happen? The cell membrane and other membranes are broken into pieces. They are not being actually dissolved. They are broken into pieces. And they get separated along with the polysaccharides. Then we have, for example, the proteins, the macromolecules and nucleic acids. That is why they are coming into the category of macromolecular fraction or the acid insoluble fraction because they are being separated along with that's the macromolecules like carbohydrates, proteins, and the nucleic acids. That's why I say the lipids are not strictly macromolecules, though they are actually being retained because of their structural organization, because they form the structural organization of the cell in the form of cell membranes. That's why we can say lipids are not strictly macromolecules. If we are considering the molecular weight, they are not strictly molecules, actually the macromolecules, simply micromolecules. Now, what do you mean by acid insoluble fraction? Acid, what is called acid soluble pool or fraction. So the cytoplasmic composition represents acid soluble fraction. Whereas you have just now with the macromolecules and you have the various organelles of the cytoplasm, they represent the acid insoluble fraction. So actually the composition of the cytoplasm represents acid soluble pool, whereas the cell membranes and all other organelles, they represent the acid insoluble fraction because they're not being filtered, they're being retained while they're being strained through a cloth. So imagine that, just simply don't forget, lipids are not strictly macromolecules based on the molecular weight, based on the retention volume, based on their structural organization into the cells. They are considered as macromolecules. Then we are considering almost all the different chemicals, the biochemicals, for example, carbohydrates, proteins, fats, etc., including the inorganic substances. Of all these ones, if you are considering which is the most abundant, that is chemical, found in living organisms, it is none other than water. So the water is the most abundant actually chemical in terms of actually you know that when we are taking cytoplasm, nearly 92% of cytoplasm is found on water. If you just burn the whole body, you can get only ash in the form of only grams, not in kilograms, all being just being sent out by means of oxidation process. What we have seen, the ash is nothing but just a boat, just a fish on, not actually men. So from the abundance point of view, what is the most abundant chemical in living organisms? Now, let us see one by one the various types of the macromolecules. To begin with, we'll start with just polysaccharides. Polysaccharides. So these are all macromolecules. You know that one found in acid insoluble fraction. So these are all long chains of sugars. If you take the polysaccharide, they are being formed of long chains of sugars. And if you are considering actually the long chain, they are in the form of threads made up of different or same monosaccharide molecules as the building blocks. So they're all in the form of threads made up of same type of monosaccharides or different types of monosaccharides as their building blocks. So the building blocks of our polysaccharides are nothing but the monosaccharides or monomers are simply called as the simple sugars. Now, so I mentioned already a polysaccharide is a combination of many monomers and monosaccharides which are considered as the building blocks. Now, based on the number of carbon atoms, we can classify the monosaccharides into trioses, having 3 carbon trioses. having three carbon compounds. For example, G3P, glycerolic 3 phosphate, and also you know that one just dihydroxyacetone phosphate. So these are all trioses. And also we have based on the number of carbon atoms, the second one tetroses, erythrulose. Then we have the pentoses in the form of ribose and deoxyribose sugars. And finally, we have the hexoses, the major abundant, that is what is called the simple sugars in nature. They're nothing but the hexoses having just the six carbon. For example, glucose C6H12O6, or for example, in the case of pentoses C5H10O5, or in the case of, for example, tetroses C4H8O4. So anyway, we have actually, based on the number of carbon atoms, we have trioses like dihydroxyacetone phosphate or phosphoglycerolide, and secondly, tetroses, erythrulose, etc. Pentoses, we have the ribose sugar and deoxyribose sugar, the units of nucleic acid, and hexoses like glucose, galactose, and fructose. So here I represent the monosaccharide having six carbon compounds as skeleton. I am not going to take actually the what is called the structural aspects. We are talking about only the applied aspect related to the biochemical aspect. So glucose, galactose, and fructose. The skeleton is different in different categories. You know that one, and they are arranged differently. And mainly these are all hexoses, the most abundant sugars, and they are responsible for making the formation of many united polysaccharide components. A number of monomers joined together to form a polysaccharide. Now this is the pentose sugar, the most important component of you know that one, the ribose sugar and deoxyribose sugar, the most important components of nucleic acid. So structurally there is only one difference. In the case of ribose sugar, you see that one we have the hydroxyl group attached to the second carbon. So number 1, number 2, number 3, number 4, number 5, you see that 5 carbon compound. And now in the case of deoxyribose sugar, instead of just actually this is for ribose sugar. And for the deoxyribose sugar, we have just in this position, instead of hydroxyl group, we have the hydrogen group. That is what is happening. That's what they call deoxyribose sugar. 2-deoxyribose sugar, because it's happening only the second carbon atom of the pentose sugar. So these are all the examples of pentose sugars, and also what we have the biologically available form of the monosaccharides in the form of hexoses. Now, the first polysaccharide. We have a number of polysaccharides, for example, cellulose, starch, we have glycogen, and also chitin, some other substances. We'll have it. So mucopolysaccharides, etc. We'll start with cellulose. You know that one, it is a homopolymer. So I am using the word protein is not a homopolymer because it is being formed of different units. A homopolymer is the one being formed of similar units or similar monomers. So the cellulose is made up of only glucose unit. A number of glucose units joined together to form a long chain of cellulose. That's why it's called as a homopolymer. So it forms a structural organization of a plant cell. It is a constituent of, you know that one, the plant cell wall. Cell wall is made up of only cellulose. And even if you are getting the paper just from obtained from the plant pulp, we are making the paper from the plant pulp, and also we are getting the cotton fiber, and all these things are also cellulosic in nature. The paper from paper pulp, and also just adding the cotton fiber, all are cellulosic materials. And I mentioned it is a long chain. The chain is unbranched, made up of a number of glucose molecules. It's composed of long unbranched chains. I mentioned just that this is very important. So a long chain of glucose joined together to form a polysaccharide cellulose and never branch. Now, what about the importance of this one? It is highly insoluble in water and also resistant to what is called hydrolysis. It cannot be broken easily. It cannot be broken. That is why we cannot have the ability. We see that one, we have no ability of digesting cellulose because we don't have the enzyme cellulase to do the hydrolysis of what is called cellulose. So it is highly resistant, highly insoluble and resistant to hydrolysis. Suppose you know that when the protein is partially broken, we have received the what is called the peptones and finally the polypeptides and ultimately we have received the amino acids. The same manner, while we are digesting the cellulose and partial breakdown and partial hydrolysis, a disaccharide made up of two units of cellulose is obtained, what is called cellulobiose. So cellulobiose is an example for disaccharide which is resulted due to partial hydrolysis of cellulose. And now it is similar to what is called a disaccharide maltose. A disaccharide maltose, the one which is received during the partial hydrolysis of starch. So when starch is broken, we have received maltose. Similarly, when just when what is called the cellulose is actually broken on partial hydrolysis, we receive a disaccharide cellulose. So this is one. Now in our fecal matter, so normally when you have more cellulose emitted, then it is called roughage. Even the waste product is called roughage. So the cellulose material forms the bulk of the fecal matter. The cellulose material forms the bulk of fecal matter. We have also another type of cellulose found in plants, what is called hemicellulose. Hemicellulose. In some cases, even the case of fungal forms. Now, agar, the one which is obtained from algae, used as a what is called medium for the culture. So it is a hemicellulose. So normally, actually, doctors are providing this agar just in relieving constipation. When agar is taken inside, as it contains cellulosic material, it just actually prevents constipation and promotes bowel movement. What even by hemicellulose in what way it is different from cellulosic material? So hemicellulose, cellulose purely made up of glucose. Whereas the hemicellulose is made up of not only glucose but also actually galactose, xylose, arabinose, rambose. So it is being formed of different types of sugars. Cellulose made up of only one type of sugar, namely glucose, a monosaccharide. But this hemicellulose is made up of not only glucose but also galactose, xylose in higher concentration, and also ribulose, mannose, etc. So these are all the different components found in hemicellulose. That's why it's called hemicellulose. So it is a heteropolymer, whereas cellulose is a homopolymer made up of only one type of unit, the monosaccharide, the glucose. Whereas this one, hemicellulose, made up of actually different monomers. Now here is a structure. So a long chain of cellulose. So on partial hydrolysis, you can see just now this is actually a cellulobiose, a disaccharide which is being formed as a result of breakdown of cellulose partial. So partial hydrolysis results in cellulobiose made up of two glucose units. And you see here this is a cellulobiose, a portion of the cellulose I represented. So here you see that one a glycosidic linkage, a bond formed between two monosaccharides is called glycosidic linkage. It's normally formed between what is called the hydroxyl groups, just between the sugar molecules, and that results in glycosidic linkage. So the linkage normally found in the case of sugars either in polysaccharides or any other components behind the glycosidic linkage. So on partial hydrolysis, we receive the cellulobiose similar to what is called the maltose of starch, which is resulted as a result of partial hydrolysis. Now, when iodine is treated, actually, when we can say when cellulose is treated with iodine solution, it doesn't take blue color, unlike starch. When starch is treated with, you know that one iodine, the iodide starch, actually the starch, the one which is iodized with iodine solution, it becomes black or blue in color. What is the reason for that? So the reason for that one is a long chain, it doesn't form helices like this. The cellulose normally doesn't form helices. So that what will happen, it cannot hold iodine. Normally we can have iodine that is being held by starch in the helices. In the case of starch, we have helices formed. So the iodine being held by these pockets. But in the case of cellulose, it's a long chain, no helices, so that it cannot hold iodine. So it cannot give reaction with iodine. It cannot give just actual reaction with iodine. That is why that we do not get a blue color. This is because of the absence of helices in what is called cellulose. So as time has completed, so I am concluding my part. So if you ask any questions or pose the questions, I'll answer it. Thank you. Class is complete.